Welcome to the second part of lecture 9. So, in this lecture we have learned what is an edge cover. Now, we will prove a theorem stating that the size of minimum edge cover is plus the size of maximum matching is equal to the number of vertices. So, edge cover you must have noticed that it is the set of edges which covers all the vertices, whereas the vertices is vertex cover is that it is set of vertices which cover all the edges. Okay. So, there is some similarity. Let us prove this theorem which says that the number of the size of maximum matching plus the size of minimum edge cover is equal to the number of vertices in the graph G. Okay. So, I have stated this theorem in the previous part of this lecture. Let M be a maximum matching. Maximum matching. So, using this notation, so M is basically alpha prime maximum matching in G. So, cardinality of M is equal to alpha prime G. Now, starting with this maximum matching, we will construct an edge cover. So, we will construct an edge cover L as follows. So, I just referred the previous example again to explain this theorem, the proof of this theorem. Well, so this is the graph G, and we know that this is a maximum matching. So, this is my M, A, B, C, D, E, F. Okay. Now, the matching M covers 2m vertices of G. This is true because here my matching M is of size 2 and it covers 4 vertices. So, it covers this vertex, this vertex, this vertex and this vertex. This is true because matching is a collection of disjoint edges. So, it will cover 2m vertices of the graph G. So, n minus 2m vertices are left uncovered, right. So, here n minus 2m means n is equal to 6 here. So, n minus 2m is equal to 6 minus 4. The 2 vertices are left uncovered. So, those 2 vertices are basically this vertex and this vertex. These 2 vertices are left uncovered. So, I have to find now we will use one edge to cover one vertex. So, if we use one edge to cover one vertex, that means I will use this edge to cover this vertex and I will use this edge to cover this vertex. Then that I have to use this many edges in my edge cover to cover this many vertices. Then the total size of this edge cover is less than or equal to m, that is these two edges, plus I am using this many n minus 2m edges for n minus 2m uncovered vertices. So, n minus twice of m. So, I got edge cover L, which size is less than or equal to n minus cardinality of m. So, this implies that cardinality of L plus the cardinality of m is less than equal to n. So, this starting from a matching, we got a edge cover, and from there we concluded that the cardinality of the minimum edge cover plus the cardinality of the maximum matching is less than equal to n. So, next we start with the edge cover. Let L be a minimum edge cover. Okay. Well, so the minimum edge cover for this graph, we know that minimum edge cover size is 4. So, the minimum edge cover consists of this edge, this edge, this edge and this edge. Well, so what it says is that since removing any edge from L yields an uncovered vertex each edge in L has an endpoint of degree 1 in VL. Okay, so what is this VL? VL is basically the subgraph. If let me refer this example again. So, L consists of the edges AD, BD, EC and FC. Now, what I mean by this VL? VL is this graph. Simply the graph consists of these edges only. So, AD, so this is A, B, C, D, E, F. This is A, D, B, D. E, C and F G. So, this is the graph V L. So, it says that since removing any edge from L yields an uncovered vertex, there is no unnecessary vertex because this is a minimum edge cover. So, if you remove, there is no edge in this graph such that both the endpoints are of degree 2, then basically you can remove that edge from the edge cover. So, you can see that every edge in L or in this graph has an endpoint of degree 1. So, it can't happen that there is an, in the VL graph is like this, there is an edge here. So, this edge both the endpoint of degree 2, that is not possible, right. That is easy to understand. So, this implies, so this property that every edge has an endpoint of degree 1, this implies that the graph VL consists of disjoint stars. I have not said what is star graph yet. So, for example, this is a star graph. It's a tree, but it's also a tree, of course, but tree can have an edge like this also, but that is not allowed. So, star means this property that each edge has an endpoint of degree 1. So, this is a star. So, this is also a star. This is also a star. This is also a star. So, this implies that VL consists of disjoint stars, and the number of components of VL is V minus L. So, this is also not difficult to observe. So, this is equal to n minus L. You think of the result that we proved in case of tree, that a tree with not tree, a forest with n components, or say a forest with n vertices and k components has n minus k edges. So, that will be helpful to prove that the number of components is n minus L here. Okay. So, now what we do is that now we construct a matching M of size n minus L by choosing one edge from each star. So, here I have two stars in my example graph. So, this is one star, this is one star, the other star is this one. So, once I have the stars in my graph VL, this is construction technique. So, you are given a minimum edge cover, from there you are constructing a matching, and this is the construction technique. So, what you do now is that from each star you just pick one edge, you can pick this edge no problem, you can pick this edge also from this graph, from this star. So, you will get a matching of size 2, right. So, this is the construction technique stars in VL. Okay. So, what you got is that you got a matching, so the matching size, you got a matching of size n minus L, but the maximum matching could be greater than equal to n minus L, and this gives that the cardinality of M plus the cardinality of L is greater than equal to n. So, before we got that this is the cardinality of L plus cardinality of M is less than equal to n. Now, we prove that the cardinality of L plus the cardinality of L is greater than equal to n. So, finally, combining these two we get that the cardinality of M plus the cardinality of L is equal to n. Okay. So, so what we have done is that we have learned the definition of edge cover, and then we have realized that finding edge cover, it is a minimization problem, because if you just include all the edges in the graph, it will be an edge cover. So, finding minimum edge cover is the optimization problem here, and we observed that the size of minimum edge cover plus the size of maximum matching is equal to the number of vertices. So, next we solve a problem which combines sort of matching vertex cover, slightly complicated problem maybe. Let G be a bipartite graph, A union B be a bipartite graph, and delta G or just delta is equal to this is see this is S is a subset of A and neighbor of S, we understand all these things in G. We look at their difference. What is the Hall's theorem wants is that this has to be greater than this one, but if it is not greater than, if it is less than, suppose this is greater than this one, then what size of matching you can get. This is all about this problem basically. So, and you compute all these differences and take the maximum over all S in A. Okay. Prove that maximum matching size, the notation that we have used, that alpha prime G is the notation for maximum matching size of G is equal to the cardinality of A minus delta. So, to relate this problem with the first problem that we started, that there is a set of 4 girls and a set of 5 boys, and there is some preference list for the girls and the boys, and there if you remember, suppose now I denote the boys side as A and the girls side as B as far as this example, this problem is concerned. If you see that the 5 boys, suppose that is my set S, and then they collectively prefer 4 girls, right. So, there this delta will be 1 because you are considering this S to be the set of all boys and N S is the set of all girls that they prefer collectively. So, there it is, this is 5, this is 1. So, you will get a matching of size. I said A is the set of boys for me now. Okay. Now, we prove this theorem or this problem, we solve this problem. Let S be a set such that for which this maximum is attained, such that delta is equal to cardinality of S minus N G S. We said you take maximum over all S and C, and so here we are assuming that S is that set for which this is maximum. Okay. So, so proving the maximum size matching is same as you prove that the minimum vertex cover is A minus delta, and since in case of bipartite graph we know that maximum size of a matching is equal to the minimum vertex cover. So, if you can prove that the minimum vertex cover in this case is A minus delta, so you are done basically. So, this is my set A, this is my set B, and there are some vertices here in A, some vertices there in B. Okay. And this set, this is my set S, and this is my set say N S. Okay, no, I want to mean that my S set is bigger. So, so this is my set S and this is my set N S. Okay. Now, you said this quantity, this is say Q star, I am trying to construct vertex cover. Q star is equal to A minus S. A minus S is this vertices, this plus this, union N S, right. So, now it is so A minus S is this plus this and this one. It is not difficult to observe that Q star covers all the edges of G, because the so the neighbor of S is here. So, all these edges will be covered by N S, and the remaining edges will be covered by this part, right. Basically, it is taking the whole A, but this slice we take for this, instead of S we take the N S part here, because N S is smaller than S. Okay. So, this Q star, what is the size of this Q star? Q star is A minus S, cardinality of A minus S plus n s, and this can be written as A minus S plus n s, right, and this also you can write as A minus S minus n s, and we know that this is delta. So, this is equal to A minus delta. So, beta g is the notation for minimum vertex cover, that size that we have used. So, we have constructed arbitrarily a vertex cover. So, the minimum vertex cover size is less than this one. Okay. So, we all agree with this one. So, we have to prove that beta g is equal to this one, which is same as proving that beta g is the minimum vertex cover size, which is same as the maximum matching size. So, proving that beta g is A minus delta is same as proving the maximum matching size is equal to A minus delta. Now, let Q be a minimum vertex cover of G. Then if Q is the minimum vertex cover, then of course, A minus Q is the vertices in A minus Q is not in vertex cover. So, well, so Q has some part, this is my A, this is my A, this is my B, and some of the vertices here are part of Q. So, A minus Q are the remaining other vertices. So, this is not part of Q. Suppose Q has these two vertices from A and some vertices from B, right. Well, so the edges incident to A minus Q, that means the edges from these vertices they must be incident to A minus Q are covered by B intersection Q. So, these two vertices are basically A intersection Q, and these are part of Q, the square vertices. So, these are basically B intersection Q, and the edges from A minus Q, they must be covered by B intersection Q, because Q is a vertex cover. Okay. So, the neighbor of A minus Q, slightly complicated problem, but you should be able to understand that the neighbor of A minus Q, which all the neighbors must be a subset of B minus Q, because whatever edges are coming from A minus Q, they are covered by B intersection Q. So, all the neighbors of A minus q must be a subset of B intersection q, and this is a very good observation, and from there the result will follow now. Now, it is mostly an algebra. You compute the cardinality of n A minus q. Okay. This is less than equal to the cardinality of B intersection q, right, which is equal to q minus q is the total vertex cover, and B intersection q is this part, and this part is let me make them red. So, this is A intersection q, and these are the vertices of the vertex cover in the B part. So, B intersection q is q minus A intersection q, no problem, and from here this is equal to, I can write q minus, now A intersection q I write in this form, A minus A minus q. This is also easy observation, right. Now, let me denote this. See, A minus q is just a subset of A. Let me call it S equal to A minus q, which is a subset of A. Now, from here what I can say that now just from here I just replace A minus q by S. So, the cardinality of n s is less than equal to this is the cardinality of minimum vertex cover. So, I will use the notation B g for that. This is B g, right, minus not B, beta g minus A plus S, right. So, from here what I can write is that beta g is greater than or equal to cardinality of A minus S minus n s. Okay. And this implies that this is cardinality of A minus, and you note that this quantity we have assumed this is equal to small delta. So, thus what we got here is that we got at the beginning here we got beta g is less than equal to A minus delta. Now, we got beta g is greater than equal to A minus delta. So, this is say equation 2, and combining these two we get thus beta g is equal to A minus delta. Okay. Now, beta g is same as alpha prime g, because alpha prime g is the notation for maximum matching. So, proving that the size of minimum vertex cover is cardinality of A minus delta is same as proving that the size of maximum matching is equal to A minus delta. So, we have proved that the size of maximum matching in this case possible is cardinality of A minus delta. Okay. Thank you very much.